Okay, today we're going to be talking about the physics of ice skating. So just before we get into any of the physics behind it, we should just maybe know what we're dealing with. So just real quick. All right, so maybe you noticed something about the spins already, but we'll get into all of that. But first, we have to have a little bit of background, in which case you need to know two variables. So the first is moment of inertia, which we kind of talked about for linear motion, but basically then it really only depended on mass. But now we have radius too, which is going to be a huge factor now because it's harder to make a mass rotate around an axis that it's farther away from versus one that it's closer to, which you can see in the diagram to the right when you just have regular equation for moment of inertia with no variables altered, and you just say the radius is 1 and the mass is 1, then you find out that inertia will be 1 originally, but when you double the mass, the moment of inertia becomes 2, and when you double the radius, it becomes 4. So we already can tell that radius is going to play a larger role in this than mass is going to, and that just plays into the whole little importance that I placed on the equation for the squared on the left, because when you double um, the radius, it actually quadruples the moment of inertia total, and that's also why a slight change in leg position for an ice skater will have such a huge impact on speed. And then the other equation that we will need to know, or the other variable that we'll need to know, is angular velocity, and the symbol for that is a lowercase omega. I don't know if anybody's ever really seen that before, but there are two equations for this. The first is velocity over radius, because the tangential velocity of any point on the circle that it's rotating on is proportional to that point's distance from the axis of rotation over the radius from the radius of the distance from the center towards that point. But since it's also the rate of rotation, which is the rate at which the angle changes, another equation that you could potentially use is the angle covered over the time it took to cover that angle. So that's really all you really need to know about this one. Okay, now we're going to get into the main principle behind spins, which is the conservation of angular momentum, or L. So it's analogous to linear momentum in the fact that it's just momentum of an object, and also that has a principle of conservation, but it's now taking it to another step where it factors in the axis of rotation. So the equation for this is going to be L, or angular momentum, equals the moment of inertia times angular velocity, which is, again, the lowercase omega. And you really just need to make sure that you know that L is a conserved quantity. So considering the fact that angular momentum is a conserved quantity and therefore must stay the same unless acted on by an outside force, like friction, you can start manipulating the variables to a certain extent. So in general, with rotation, you can apply torque to something speeding up, such as like a spinning top, and its angular momentum will increase. But for that scenario, frictional torque is what eventually slows the top down. However, in this scenario, there's such low friction between the blade and the ice that we just assume that there is no frictional torque, which means that altering one variable in the equation will cause the other to compensate. So now we'll get into how this relates to the ice skater's actual movements.
Okay, so how does this relate to Miss Katie, Miss Figure Skaty? Well, when her legs are stretched out, the mass is further from the axis of rotation, and that is the dotted line in the middle, as you can see right on this graph or this picture. And this is the initial position on the momentum bar chart right over here. This one is the initial. Then she tucks in her arms and legs, and which draws the mass closer to the center of the rotation, and that makes the momentum of inertia decrease. Since the momentum is conserved, the angular velocity will increase, so she will go faster. As you can see in the final, her angular velocity increases all the way, and the ability to resist inertia decreases because her mass is closer. So you're telling me that Katie knew physics for years? Yes, Katie was a genius. She knew that. The moment of inertia decreases on radius, and then when she tucks in her arms and legs, radius of mass to center of rotation, it decreases, which decreases the moment of inertia. And then because of the conservation of angular momentum, angular velocity must compensate by increasing. So the I decreases and the angular inertia increases. So here's a video example. You can see that the number next to the lowercase omega increases as the distance between the mass and the center of rotation decreases, and that is because the angular velocity it speeds up the closer it gets to the axis of rotation. Yep.
Okay, so since we went over spinning, the next step is to look over the next important element in figure skating, which is jumping. And to do this, we're going to revisit Newton's third law of motion, which states that if object A exerts a force on another object B, then the object B would exert an equal and opposite force in object A, which means it would exert a force with an equal magnitude in the opposite direction. And just like on ice, this is how people do it on Earth too. So, if you exert a force into the Earth by bending your knees and pushing downward, the Earth would exert an opposite force up into the air, which helps people jump on Earth. Knowing that, we can learn about jumps on ice. And to do that, and to learn about how skaters push enough force into the ice, it's really important to look at the blade of the shoe. So this is a blade, and as you can see, it is curved over here. So one way that a skater can push enough force into the ice is by shifting their weight using that curve, with putting their toe on the ice, and then using that force to push themselves upward. Another way that skaters also take off the ice by exerting enough force into the earth is by pushing their toe and shoving it into the ice, and with that force, they're also able to jump off. So, as you can see on the diagram on the slide, is an example of someone pushing weight by shifting their ball of their foot onto their toe. And as you can see, is an example of a third law pair, since it has a force of the skater pushing on the ice, and then an opposite force of the ice pushing up onto the skater, which will create that jump. And this force diagram is an example of a skater before takeoff representing a third law pair. So, since we figured that out, we can look at the different takeoffs of two famous skaters. On the left is Yuzuru Hanyu, who is famous for his quad jumps, which is 4 rotations in the air. So in the left picture, you can see him push his foot onto the ice, and that's how he exerts enough force downward to propel himself upward. And then on the right, we have Mirai Nagasu, whose historic triple axel made big applause at the 2018 Olympics. And she does the thing where she shifts her weight onto her toe to propel herself upward. So after we learned about third law and angular momentum, we can learn how we can put them together to show how a skater creates one of these huge jumps. So in the diagram, the skater puts their foot into the ice, and this is an example of the third law in action, and then creates that angular momentum by lifting their knee up into the air and tucking in really quickly to increase that angular velocity. And because they do this, they're able to rotate in several revolutions and then are able to land afterwards after they've completed the revolutions. And this takes years to master. This is why lots of people can't even do the maximum amount of spins in the air, which is 4, and only a rare few are able to do that. So, the next thing in the slide is a video of me when I was 9 years old, trying to learn how I can utilize the angular momentum to spin me in the air. So, you can see my arms tucking in really quickly to try to get me around as fast as possible, and me pushing up into the air by exerting force downward into the ice. So I hope this gave you a broader understanding of the sport, and I hope you enjoyed.